So, my name is John Walrond. This course is BMS 300, Principles of Human Physiology. My office is in 235 Physiology. The Physiology building is that squat T-shaped building on the corner of Lake and Center. It's sort of one of the ugliest buildings on campus, but that's where I live. My email address is john.walrond@colorado.edu, but a good way to get in touch with the GTAs is through csubms300@gmail.com. There are 4 GTAs for this course: Haley Hullings, Josh Hayes, Kendra Jacobson, and Andy Fisher. And we set up this email address a couple of semesters ago now, and it works pretty well. If you simply send an email to this address, these 4 GTAs will be monitoring that email. And so you don't have to get in touch with each of them individually. Just go to this address, and then you'll get a response from one of the 4. And that way it distributes the load a little bit better. Now, what we're going to do here is I'm going to lay out a kind of outline. And this is a typical way that I set up my lectures. That is, the 2 flanking boards will have an outline of the material that will be presented that day. And I'll begin each lecture with about a 5 to 7 minute discussion of what's on the board. Now, I advise you to copy this down and pay attention when I'm reviewing this material. Because one of the secrets of teaching and learning is that there are only about a half dozen or maybe 8 ideas that you can possibly cover in a 50-minute lecture. So the major concepts that I want to convey during a particular lecture will be on these outlines. And if you review the outlines from the videos, and we'll talk about the videos in a minute, if you review the outlines, you have a pretty good idea of the ideas and concepts we're trying to get across in those lectures. Now, the rest of the lecture is going to be predominantly just the details to fill in the concepts we spell out in the outlines. And this is the beginning of the outline of what we'll talk about today. But before we get to the material, let's spend a few moments discussing the syllabus. Now, you all have copies of the syllabus. They're in Canvas on the homepage, and you can read it as well as I can. But there's some points I want to make here. First is simply the first sentence talking about the objectives of the course. And I think it's important to spend a couple of minutes just telling you what the philosophy of the course is and some of the outgrowths of that. This is a very broad-based course. It's an introductory course to physiology. We're going to cover a whole lot of material in here. It's going to be a mile wide and an inch deep. So what we'll be doing is covering the surface of physiology. But hopefully this will give you the background of material that you'll need to go on into other courses, whether it's in exercise and health sciences, whether it's in biochemistry, whether it's in biomedical sciences. This will be a foundational course for other upper division classes. So we try to cover an enormous amount of material here. And in the next 15 weeks, I'll be talking to you about a whole lot of different things. And there's going to be a tremendous amount of information that's going to be coming at you. There will be new vocabulary. There's no way around that. But some students think if they memorize the vocabulary that they're done with the learning for the course. But that's not my attitude in this course. My attitude is that the details, the details are simply there to illuminate the bigger ideas. They're there to show you the way to the concepts. And the way I try to teach this course is through a series of stories. I try to generate stories, and physiology is particularly conducive to telling stories. There are all these stories in physiology. We'll start with water, and by the time we get to the end of the class, we'll be talking about development and human reproduction. And all of the way, we'll be picking up new ideas and new concepts and new vocabulary to bring us to the next series of topics. So there's a lot of information you'll be picking up along the way. We'll be building it one to the next. And part of that will be vocabulary. That's unavoidable. But I'm trying to help you learn the vocabulary so then you can use it, and use it to tell stories. And if all you do is memorize what I've told you, you won't hold on to it very long. And the way the course is designed is we're trying to get students to use knowledge as a kind of tool to solve novel problems. And when we come to the exams, the exam questions will hopefully be the kinds of questions you've never seen before. They will have been covered in class. The ideas and the concepts will have been described, and you'll have learned about them. But the particular question may not be something you've seen before, but you'll know enough to solve the problem. Now, the exams will be divided up into 32 multiple choice questions and then another 20 points from fill in the blank. And I'll use this to try to illustrate how I think it's best to learn in here. The fill in the blank questions will be 20 points. There'll be 26 blanks, so you'll have some extra credit on them. And when you first look at these fill in the blank questions, you'll see a bunch of blanks, and you'll think, where do I start? But you'll read a few words and you'll get a theme. And then once you get the theme, you'll put the story together. And what I'm trying to do with these fill in the blank questions is get you to be able to tell a story. So there'll be a story that you have to find the nouns and verbs to fill in the blanks. And then once you've learned this material by telling stories, when you look at the multiple choice questions, you won't just read the question and look for a word in the question and look for a word in the answer list and try to match them. You'll read the question and say, what idea is this trying to get to? What's the concept we're trying to illuminate here? And then you call up the concept, which may be from the flanking boards, and you start in your internal dialogue telling that story. And as you tell the story, then you'll find the sentence or the phrase or the word that's in the answer list, and that's the right answer. There's a trap sometimes of students getting confounded by these multiple choice questions because they read the question, they read the answers, and they all look alike. But you can walk around that problem by looking at the question, thinking what's the idea, and then starting your internal dialogue of the idea. Also, I try to write those questions that you don't have to know the list of factoids to answer it. You'll have the idea, you'll have the concept, you'll find a loose thread someplace in that question and find your way into the question to find the answer. So what I'm trying to say here is that this is not a course that is revolving around memorization. It's a course revolving around concepts. Now, it's true, you're going to have to remember the nomenclature. You're going to have to remember the vocabulary. Those are the characters in the play. They're the characters in the story. They're the characters for the plot. But it's the plot we're after, and you'll simply have to use the characters to fill in the plot. I think this is a far better way of learning. After all, we learn from the time we're children, from stories. Where grandmothers have told us stories, and we remember those stories for the rest of our lives because they're in a story form. If they're in a list form, like a telephone book, you don't tend to remember it very well. So I think that if you can formulate a way of learning this material that isn't simply reading the material and trying to memorize it, or simply watching the videos and letting it wash over you, or just coming to class and letting it wash over you, you need to engage with it. And the engagement with the material is generating and telling these stories. And I think that if you approach the material this way, it gets way easier. As an extension of that, it's often helpful to study with others. Find a study partner so that you can tell the stories back and forth. That you can use the objectives in the ebook or use the objectives on the side panels and use that as a kind of cue card to start your discussion. And go back and forth between you and your study partner so that you can work your way through these stories. If you have to, teach your cat, because it's the verbalization of the material that seems to be so important in getting it down and understanding it. Well, having said that, the grades, which are an unfortunate byproduct of education, the grades that we have to give are all based on the exams. There will be 4 unit exams and a final. Now, each of those unit exams is worth 100 points and the final is worth 200 points, so if you add that up, that comes up to 600 points. But the way the grades are determined is that we'll take the 4 unit exams and the final and drop the lowest score. If your lowest score is on one of the unit exams, we count 3 unit exams and the final counts twice for a total possible 500 points. If your lowest score is on the final, then we count it only once, add it to the 4 unit exams, and use the score in the final, which is a cumulative final, by the way, to come up to 500 points. Now, we'll add up all those points and we'll determine the grades, and then we'll go back and we'll see about extra credit, because there are a number of ways to garner extra credit points in this class. But each of these attempts to get extra credit points are not about the points. They're really an attempt to try to draw you into the material to learn it for yourselves. The first series of extra credit points will be from what we call after-lecture quizzes. So after each lecture, the GTAs will write up a short list of questions, mostly definitional questions, simple questions based on the lecture that was just given. You'll have 24 hours then to answer those questions. You can answer them from your notes, or you can go back and answer them from the videos that will be posted. And it's open note, it's open everything, but just go back and answer the questions, and there will be one for each lecture. Now, the reason we're doing this is that we found, not only in here, but also in general psychology of learning situations, that the sooner you get back to the material and review it, the better off you are. The longer the duration between initially seeing the material and then studying it, the less you hold on to it. So we're trying to induce you with a small number of points to each day go back and review the lecture, answer some simple questions, and engage with the lecture. Now, the number of points are pretty small. Each of the 4 unit exams and plus the final, each of the questions from the after lecture quizzes are only worth 1.5 points apiece for a total of 7.5 points. So again, you get some points out of it, and if you don't do it and you're on the border, you're going to be unhappy you didn't do it, but it's mostly to get you to go back and review the material. Now, the EBook quizzes are just the opposite. What we're trying to do with the EBook quizzes is introduce you to the material before the lecture. So the EBook quizzes will open on Thursday, they close on Monday, they're open over the weekend. And what they're intended for is for you to go into the ebook, read the material. The ebook is based around the objectives. So the initial part will be objectives, and then from those objectives there'll be links. Go to the links and there'll be figures and there'll be a narrative. That's the material you want to be reading. But then go back to the objectives and get to the point where you become fluent with those objectives so you can tell the story that was told in the narratives with the figures. The figures are important because they give you a kind of cartoon from which to hold on to the material. Now, if you're studying anatomy, you're studying the parts and you're looking at the parts. And I think of anatomy as being fine art. But when we're studying physiology, it really is a series of concepts. It's a series of cartoons. Where anatomy is fine art, physiology is Pictionary. Because what you're trying to do is generate a kind of symbol, a kind of cartoon, and then spin a dialogue, spin a story around that cartoon. The cartoons you can have in your own head. You'll probably generate your own. But the images that we have in the ebook are to help you start that process. But in the end, you need to be able to have an internal dialogue along with a visual image of what we're talking about. Several years ago, there was a student who had come back to school after she'd been out for years. And she said to me she knew she'd be all right in this class when she could close her eyes and take a walk through a cell. And it's true. You need to be able to have this visual image and be, with that visual image, describe what you see in your mind's eye. It helps a lot in this course. So the 2 forms of extra credit I've given you so far are the after-lecture quizzes and the before-lecture quizzes. So one is a retrospective and one is prospective. The third place that you can pick up a few extra credit points, and you can pick up a total of 5 extra credit points from going to what we call tutorials. We've been running these tutorials for years. And what the tutorials are is we have 2 students who have taken this course sometime in the past. They've liked the material, they've done well with the material, and they like to teach other students. What's more is they recognize that by teaching they'll learn. And so they get together once a week with small groups of students, usually 6, 8, 10, maybe as many as 20, and start a discussion of the material that we've covered in the last week. If you attend 10 of these tutorials through the course of the semester, that will give you 5 extra credit points. So if you add that up, it's 5 extra credit points for the tutorials, 7.5 for the after lecture quizzes, and another 12 for the ebook quizzes. So it comes out to a sizable fraction of a grade. So don't ignore them. And the tutorials we're trying to arrange so that you just don't go there and passively sit through someone else telling you what's going on. We're trying to arrange them in such a way that when you go, you open a dialogue with someone else. The tutors are there to sort of organize and guide the discussion, but we want the students to be participants in the discussion. And so we've generated these over the years, and I think they work pretty well. We've looked at some data, and students who attend these tutorials do about a half a grade better than students who don't. So it's worth your while going. Similarly, there's the 1 credit recitation. Now, the 1 credit recitation is a formal course. The tutorials are informal. But the 1 credit recitation, BMS 200, is a 1 credit course, and you get 1 credit, you get a credit for taking it. It again meets once a week with the tutors. Meets once a week with the GTAs, one of these 4 GTAs, and you'll meet with the same GTA week after week after week, and you'll get a grade for that course. The grade is based entirely upon attendance and upon the weekly quizzes, which are in Canvas. And those weekly quizzes are all open book, open note. This is not designed as a course to be particularly difficult. It's designed as a course to bring you current with the material, stay up with the material, review the material, and meet with other students to discuss the material. And again, just as with the tutorials, we've worked pretty hard to try to generate a kind of discussion atmosphere rather than a passive, you sit there, someone tells you something. Trying to engage with the material. Anything else? Any questions? Yes? So the question is, if we attend half of them, do we get half the number of points? And the answer is no. It's a threshold. You have to attend 10 to get the 5 points. And you can't attend 10 in the last week. You can only attend 1 a week. So again, trying to get you engaged with the material through the course of the semester, rather than just saying, I need 5 points, I'm going to go flat out and do what I can in the last 2 weeks. Anything else? Yes?
Are some of the tutorials online, or are they all?
Some of the tutorials will be online. And in fact, I should mention that because although you're all sitting in this room, there's another section of this course that's entirely online. And those students will have access to the tutorials through online using Adobe Connect. And so if you prefer the anonymity of attending those, then please feel free to do so. But they were originally developed for the online section, but they're open to anyone who wants to use them. A word about the optional textbook. This often comes up as a question. My view on the optional textbook is that if you really need to have a hard copy text, go and buy one, but don't buy it brand new. Go out and get a copy of Vander's Physiology from 2 or 3 editions ago. There's nothing so new that we're going to be talking about that it needs to be in a brand new textbook. And we've decided over the years not to use one of these classic textbooks because we end up assigning reading, there are pages of reading, students read it, and there's too much detail and it washes right over them. So I think it's better to, if you want to use a hard copy text, to use it as a reference text, to use it using the index. So if there's something you've seen in lecture, something you don't understand, something you want to know more about, look up that term in the index, go to the page or 2 in the book and read that material. The other place that it's useful is that it will give you an additional set of figures. And physiology is built around figures. And so if you get to look at another set of figures that look slightly different, it again reinforces the information you're taking in this course. So from that standpoint, I think it's useful. On the other hand, in our modern world, Google it. And although as an academic I don't like to push it too hard, Google really is fairly useful. And the material that I've looked at on these topics that we cover in here is pretty well covered. And so it's another voice that you can hear, another voice you can look at to cover this material. And they also often have very good figures. So just go ahead and look at them. And again, the more you can look at this material, the more you can engage with it, the more you can get away from simply passively waiting for it to come to you and go engage with the material, I think the better off you'll be in this course. Anything else?
Will there be a quiz after today's lecture?
Will there be a quiz after today's lecture? Yes, there will be a quiz after today's lecture. And the tutorials will begin on Monday. And Haley gave me a bunch of notes here. And for the tutorials, the forms to keep track of your attendance will be passed out at those tutorials. The schedule is mounted. The schedule is mounted on the homepage of BMS 300. So look at that. It's not finalized yet. It won't be finished until Sunday. But we have a broad outline of it. But be aware, it's in flux and may change before Monday. Yes?
If you're enrolled in BMS 200, you still have to go to the tutorials.
So the question is the requirements of the tutorials. You don't have to go to the tutorials. I think they're useful, but there's nothing that says you have to go to them. They're entirely voluntary. The recitation is optional as well. You don't have to take the recitation. But again, the statistics show that students who go to the recitations and participate in those discussions do better than those who don't. There's always the caveat that maybe the students who don't care so much don't go. So we don't know. But statistics say go and you'll learn something, and you'll be better for it. Anything else? Yes?
What will the first quiz cover? Next week's stuff or this week's stuff?
So the first ebook quiz will cover pretty much what we're doing this week. Because although they're designed to be looking ahead, we start at the beginning with water. And so a little bit it will be retrospective for the first week or so, first couple of them. But hopefully before too long, they'll be looking forward and introducing you to material that will come up. Yes? Those will open on Thursday. So those will open tomorrow and they'll close on Monday. Yes? For the ebook, you need to purchase that access code. For the hard copy textbook, I would say go to Amazon and buy one that's been out of print for 10 years. Anything else? Well, if not, let's get started here. So again, this is the outline that I have on the board. We'll basically cover this material today. And what we're going to talk about is we're going to talk about water. Now, we typically, in a physiology course, start with a discussion of water because it's said to be the elixir of life. All biological functions occur in a salt solution. We evolved out of the ocean. And so inside the cell, outside the cell, we're working in a salt solution, and that solution is ions in water. So we really need to have a general basis of the chemistry of water and how water functions and how it works. So we'll start here with a simple set of ideas of what is water made of? What are the components of water? Water has a molecular weight of 18. That molecular weight is derived from the 2 atoms of hydrogen and the 1 atom of oxygen. The 2 atoms of hydrogen each have an atomic weight of 1, and the oxygen has an atomic weight of 16, giving a molecular weight of 18. Now, that's a fairly small molecule. Now, it's even smaller than some of the molecules in the air around us. 79% of the air around us is nitrogen. 21% is oxygen. Now, don't memorize these numbers. These are just for reference. The boiling point of nitrogen is minus 196 degrees centigrade. The boiling point of oxygen is minus 180 degrees centigrade. If you get one of the noble gases like helium, which is really small, it has a boiling point of minus 290 degrees centigrade, which is only 4 degrees above absolute zero. But water has a boiling point, as we all know, of 100 degrees centigrade. So what is it about water, which has a molecular weight of 18 compared to oxygen of 32 and nitrogen of 28, which allows it to have such a high boiling point compared to these other molecules? The answer to that is the hydrogen bonding. Now, it's certainly true that water molecules contain 2 atoms of hydrogen covalently linked to the oxygen by a covalent bond. That is, they're sharing their electrons electrons. The electron of the hydrogen and the electron of oxygen are being shared to make a stable molecule. But what happens in water, because of the, put your phone away to appreciate it, what happens with water is that because the hydrogens contain only an electron and a positron, a proton, then the oxygen now will borrow those electrons. And because the oxygen has borrowed the electrons, it gives something, a characteristic to the molecule called a dipole moment. It means that one end of the water molecule is going to be slightly more charged than the other. One end, the oxygen end, will be negatively charged, and the two hydrogens will be positively charged. Because of this charge, you can think of this charge as tiny magnets. It's an electrostatic attraction between the positive charge on the hydrogen and the negative charge on the oxygen to form something known as a hydrogen bond. The electrostatic interaction will hold these molecules together. Now, it doesn't hold them tightly together. It doesn't hold them tightly together as does the covalent bond. But it's a bond that holds them together for a long enough period of time that between 0 and 100 degrees centigrade, water remains liquid. Now, the times that one water molecule is interacting with another water molecule is frightfully short, picoseconds. But in fact, because they interact one with another, turn around and find another, then water can be liquid at room temperature. Whereas because these molecules, nitrogen, oxygen, and helium, don't have a dipole moment, then it requires far less energy to allow them to boil. Whereas because of the interactions of the positive and negative ends, the dipole moments on the water, it takes much more energy to get those molecules to go from a liquid to a gas state. The other important aspect of water is not only simply that it's liquid at room temperature, it's also the fact that it provides a vehicle into which we can put ions in solution. In other words, the dipole moment on water allows, because of its positive end, to interact with anions. The negative charge on a chloride can interact with the positive dipole on the water. And the positively charged cations, such as sodium and calcium, potassium, can easily then interact with the negative dipole of the oxygen. It's said that these ions are hydrophilic. They're water-loving because they easily go into solution in water, and they easily go into solution in water because these highly charged ions can interact with the dipole of the water molecule. That leads to something known as the shell of hydration. Each of these anions and cations will be surrounded by a sphere of water molecules. And that sphere of water molecules is oriented in such a way that the negative end, the oxygen, will interact with sodiums, and the positive end, the hydrogen, will interact with the anions, forming a shell of hydration around all of these ions. Along with this, we'll also add in the idea of surface tension. We'll talk about what happens at the air-water interface and how hydrogen bonding is important for generating surface tension. And then finally, if there's time, we'll talk about the random walk of diffusion. Yes?
Isn't the shell of hydration called a clathrate?
So the question is a shell of hydration the same thing as a clathrate? Let me think about clathrates for a moment. Clathrates will, in fact, form with water around them. But I think of the clathrates as being different. The one case I know of clathrates is where if you have methane under high pressure, and not even particularly low pressure, it'll actually form a crystal, because the water molecules will be around that hydrophobic molecule, and the pressure and temperature will form a clathrate. That's one of the things that happened in the oil spill. In 2010, they had all of this methane coming out into the high pressure in the water and the cold temperatures, and there was a snow of clathrates. And one of the things they tried to do is they tried to put a cap on top of this tube with the oil and gases coming out of. And as they put it over, the clathrates would form and float it right off the tube. And that was something they didn't know about until they ran into the problem, and 210 million gallons of oil spilled into the Gulf. But that's a different story. So what we're going to do here now is talk about the structure of water. Water, of course, is composed of two atoms, of hydrogen and 1 atom of oxygen, hence H2O. Now, if we look carefully at this molecule, we see that we have an oxygen with an atomic weight of 16 is considerably larger than the hydrogen with an atomic weight of 1. The hydrogen, in fact, if you remember your chemistry, hydrogen is typically composed of only 1 electron and 1 proton. It's 1 electron revolving, spinning around 1 proton. So here we have a hydrogen, and here we have a hydrogen. So this hydrogen is now covalently linked to the oxygen. This is a covalent bond. This says that the electrons are shared. There's an orbital around the oxygen and a single orbital around the hydrogen, and these electrons are shared in those orbitals. But one of the characteristics of water, one of the things that makes it unique, is that this electron sharing isn't even. What happens is because of the mass and charge on the oxygen, the electrons tend to spend more time around the oxygen than they do around the hydrogen. You can think of this as though the oxygen has borrowed or stolen the electrons from the hydrogen. Now, it's true we don't know exactly where in this cloud of electrons the electron is from these hydrogens. Dr. Heisenberg told us that we can't tell exactly where in space and time those electrons are. But on average of time, these electrons are spending more time around the oxygen than they are around the hydrogens. Because the electrons are spending more time around the oxygen, this gives the end of the molecule what we call a delta negative, a partial negative charge. Because the total charge on the molecule has to be neutral, that means this excess of negative charge out here leaves a partial positive charge on the hydrogens. So now we have this molecule, because of the characteristics of the way the electrons are being shared, this molecule has an uneven distribution of charge, giving rise to a negative end and a positive end of the molecule. These negative and positive ends are said to be a dipole, or a dipole moment. Well, this has important implications when we put water molecules one with another. So that if we now imagine water molecules hanging out close to one another. So there's an oxygen. Here are the 2 hydrogens. There's another water molecule down here. There's its oxygen, covalently linked to the 2 hydrogens. Put another one in here. Covalently linked to the 2 hydrogens. Now, because of the charge, this hydrogen has a slight positive charge on it, and the oxygen has a slight negative charge on it. You can think of these charges as tiny magnets. So now there's an electromagnetic attraction between the negative end on the oxygen and the positive end on the hydrogen. This electromagnetic attraction has a name. It's called a hydrogen bond. So again, the covalent bonds are electron sharing. The hydrogen bonds are simply due to the electromagnetic interaction between the ends of the molecule. But this now becomes important for the characteristics of water because this negative charge and this positive charge will interact ever so briefly, maybe only a picosecond or 2. And then this water molecule will change its position and interact with another neighbor. And its neighbor will interact with another neighbor. So the electromagnetic charges here are now attracting one another and holding these molecules more or less together. Now, don't memorize these numbers, but I found it sort of interesting to look at these. That a typical, put it up here, a typical hydrogen bond is 1.97 angstroms. This is 0.197 nanometers. A nanometer is a billionth of a meter. These are tiny, tiny distances. And these average distances of 1.97 angstroms don't last very long. They switch around. But one of the interesting characteristics of water is that if we take enough energy out of the system, if we reduce the vibrational energy of these water molecules, eventually they slow down and they spend more time in their hydrogen bonded state. And if we take enough enough energy out of the system, these hydrogen bonds become more or less permanent. That's when we form ice. And when we form ice, when we take enough energy out of the system and we form ice, this hydrogen bond length gets a little bigger. Goes from 1.97 to just a little bit longer. It seems like an insignificant change, but it has enormous effects. Because what it means is that when water freezes, and because the hydrogen bond lengths become greater, water expands when it freezes. We know this intuitively. If you go home today after a cold day, well, not so much today, if you go home after a really cold night and you didn't have the heat on in the basement where the water pipes were, you know what's going to happen. They're going to burst. And the reason they're going to burst is that when water freezes, it takes up a larger volume. That's bad news in your water pipes. But in fact, it's good news for life on the planet. Because it means because water is less dense, because of this extremely small increase in the bond length and the reduction in the density of the water, when it freezes, ice floats on water. If ice sank instead of floated, we'd be living on a ball of ice here on this planet. But because it floats, then with the seasonal changes, it can melt and refreeze. It's an important aspect to life here on Earth because of this weird characteristic of water where the bond length, actually the hydrogen bond length, increases at the time of freezing. So any questions up to here? Okay, back here first.
So just to clarify, hydrogen bonds are between molecules and covalent bonds are
So the fair statement is, yes, that the covalent bonds are within the molecule and the hydrogen bonds are between molecules. We're going to find hydrogen bonding coming up in a number of different places in the next few weeks. We're going to see that not only is it found in water, but it's also found in protein structure. We're going to find that it's found in the way the two strands of DNA are held together. And so all of this comes about because of charge interactions. And you're right, those are between molecules, whereas the covalent bonds are within the molecule. Yes?
Do the partial charges become collective over time with hydrogen bonds and increase the strength of the bond itself in molecules?
So do the hydrogen bonds become, well, they don't really become, I was going to say, they become stronger when you freeze the water. So because they just don't, but they don't really become stronger, they just have less time to move around. They don't switch. And the total charge on the water, so if you ask what's the charge on a glass full of water, that's 0. But if you look at the individual molecules, then each molecule has this dipole moment on it. But in total, because in average, there is no charge. I'm not sure that answers your question, though. All right. Anything else? So from this idea of the water molecules interacting through hydrogen bonding, I want to raise the idea of another concept. And this is a concept we're all familiar with. This is the idea of surface tension. And we can explain surface tension at the air-water interface because of hydrogen bonding. So if we imagine this is a beaker of water, And if you've ever looked at a beaker of water, a graduated cylinder of water, you remember that it has a sort of arc to it called the meniscus. And the reason the meniscus exists is that the charge in the glass is such that the water molecules are interacting with the charge in the glass, and that gives us a little upturn at the end of the meniscus. But here within the water column itself, there is also an interaction between water molecules. So that, using our convention, at the air-water interface, there's an oxygen. There's a hydrogen. There's a hydrogen. This water molecule now can interact with a neighbor. There's a hydrogen. And so now the dipole moment, the hydrogen bonding here, will be from the oxygen of this water molecule to the hydrogen of this water molecule. So there's a hydrogen bond. And all along this air-water interface, these molecules are interacting one with the other to form surface tension. Now, you can overcome that surface tension by simply heating the water. If you heat the water to a boil, you put enough energy in here that there's so much energy that the energy of the hydrogen bonds is overcome, and the water evaporates, it leaves, turns to steam. And we do that at 100 degrees centigrade at standard temperature and pressure. It's a little less here at our altitude where we live, but nonetheless, you can put enough energy in it to where you overcome that surface tension. But the surface tension is a real force. And you can see the surface tension as a force if you go out on a summer's day and simply go down to a pond and look at the insects that are living on that pond. There are some insects called water striders that literally walk on water. The other name for these bugs is Jesus bugs. And what they have is at the end of their 6 legs, they have these very fine hairs called setae. So that increases the surface area at the ends of their legs. But because of that increased surface area, they can stand on the water. They can stand on the surface tension. There's the gravitational pull on that insect is less than the surface tension holding them up. You can do a cruel trick. You can take that water strider into your house, put it in a bowl of water, and it will stand on that surface tension just fine. But now take a little bit of dishwashing detergent. And what the dishwashing detergent does, and we'll see a little later, is it's amphipathic. It lives both in hydrophilic world and hydrophobic world. And what the detergents will do is they'll get in between these water molecules. They'll intercalate between the water molecules and lengthen the hydrogen bonds. And by lengthening the hydrogen bonds, the energy of the interactions, of the magnetic interactions of these molecules is less, and that poor water strider will sink to the bottom, simply because you've broken up the hydrogen bonds between neighboring water molecules, reduced the surface tension, and now there's not enough surface tension for that insect to stand on, and it sinks like a stone. But simply to illustrate the importance of the interaction of these water molecules. The other idea that comes from this dipole moment is the concept of ion solubility. Ions are charged. Anions, such as chloride, are negatively charged. Cations, such as sodium and potassium and calcium, are positively charged. These molecules, which are highly charged, are said to be hydrophilic. This term, hydrophilic, comes from the Greek. It means water. Loving. Now, if we think about that, we can imagine, and we've all done this experiment, where we're sitting at home at the dinner table and we take the salt shaker and we pour some salt into the water glasses sitting in front of you. Well, we can talk about that as though we had placed at the bottom of this a crystal of sodium chloride. Now, in that crystal, each sodium ion is paired with a chloride ion. They're paired one for one in the sodium chloride crystal. But they're fully charged. There's a fully charged sodium ion and a fully charged chloride ion. Now we take that sodium chloride and we put it into water. The water molecules now are bouncing around one to another. This is liquid water. So there's a certain amount of thermal agitation in here, a certain amount of kinetic energy, where these water molecules are bouncing into the sodium chloride crystal. As they bounce into the sodium chloride crystal, they have enough energy to chip off a chloride ion or sodium ion, such that now the sodium ion goes into solution and the chloride ion goes into solution. But I think you'll recognize that since this sodium is positively charged, it will interact with the water molecule in such a way that the oxygens, the negative charge on the oxygen, is pointed toward the sodium. Then out here with this positive end, there'll be another layer of water molecules. Now, I've drawn this in 2 dimensions, but imagine it in 3. Imagine that we have a sodium ion sitting at the center, and all around it will be layer upon layer of water. This layer upon layer of water is said to be the shell of hydration. And you had a question? So does the boiling point go down or does the boiling point go up? The boiling point, the freezing point goes down. There's freezing point depression. The boiling point, I think, goes up because the water molecules are bouncing into the ions rather than being free to move out into the air. So I think the boiling point goes up, but I really need to look that up to be sure. I know the freezing point goes down. That's why you put salt in the roads in the wintertime. So now the sodium and chloride are out into solution, but let's look at the chloride. The chloride now will have the positive ends of the dipole moment interacting with the negative end of the chloride. And again, forming a shell of hydration, simply using the positive end of the dipole moment to interact with the negative chloride and forming the same kind of shell of hydration, simply with the hydrogen ion facing the chloride and the oxygen away, as opposed to the sodium ion, where the oxygen is pointing in and the hydrogens are pointing away. Now, the last moment here, let me put a couple of numbers to this. Let's say that this is 1 liter. And let's say the amount of sodium chloride here is 5.84 grams. It turns out that there are 58.4 grams per liter is equal to a mole. So there's 1/10 of a mole of sodium chloride in here. So that when this sodium and chloride goes into solution, all the sodium ions in the crystal have gone into solution, all the chloride ions have gone into solution, we have a 0.1 molar sodium chloride solution. But it's an important concept here that I want you to hold on to, is that because the sodium ions and the chloride ions have completely dissociated, that these sort of concentrations, they're not going to interact with one another very much. They're completely and separate from one another. We find that it will dissociate into 0.1 moles of sodium ions and 0.1 moles of chloride ions. Because we have complete dissociation, that means we have a total of 0.2 moles of ions in this 0.1 molar sodium chloride solution. This concept is going to be important next time when we talk about osmosis. So let's leave it there, and we'll pick up these ideas tomorrow.